Thank you for coming. My name is Wayne. I'm founder, president, and CTO of Omrise Technologies. I'm very surprised that you guys know that there's going to be this talk, and I am very sorry that the original talk got pulled and we couldn't do it. Jack Yu holds most of the material for the original talk. So today we're going to be talking about Drivesploit, circumventing automated and manual detection of browser exploits. There's a lot of slides, so I'm going to go right into it. So let's take a look at one type of browser exploit, the drive-by download type of exploit. Drive-by downloads are attacks where hackers distribute malware by poisoning legitimate websites. What's typical is an attacker would inject malicious iframes into HTML content, and the affected website essentially becomes a delivery mechanism for malware. It appears normal, and the victim do not need to click or agree to anything. They would simply connecting to the website executes the attack. For example, Aurora, that happened earlier this year. It was using IE 0-day. It was confirmed publicly by Google, Adobe, Juniper, and Rackspace. And a total of 34 organizations were targeted. And Aurora was a typical drive-by download attack. DNF 666, mass SQL injection, started since March 2010. Ended, the last wave happened about 3-4 weeks ago. And it was using initially an Adobe 0-day. And the victims included Wall Street Journal, Jerusalem Post. And in the past, it happened to CNN, GameSpot, US Treasury, Sony PlayStation, Washington Post. So let's dissect drive-by downloads. The visitor, what happens is the visitor visits an exploit server, which serves him a page plus a driver exploit. And then there's a payload, which we call the downloader. And all of these exist in the form of JavaScript, and often obfuscated JavaScript. So the obfuscated version looks somewhat like this. And here's the actual exploit. It will exploit the visitor's machine without him knowing that anything had happened. And so we call these exploits and droppers. The dropper executes, connects to a malware server, and fetches back the actual malware that gets installed in the victim's machine. And then the actual malware connects to the controller. Okay, so the question here is, who would visit this exploit website? So the key now is traffic. And so the attacker would go in and break into very big and popular websites with a lot of traffic. For example, YouTube, Amazon, etc. And these websites usually would then, in their legitimate page, include a piece of JavaScript that generate URLs. We call those URL generators. So the URL generators would then dynamically generate either an iframe or a JavaScript source pointing to the exploit server. So from May to June, and the way to do that is, for example, mass SQL injections, massively using SQL injection vulnerabilities that exist in websites. In May to June, we saw mass scale shared hosting compromise, and these included GoDaddy, Rackspace, Network Solutions, Bluehost, and DreamHost. And such an attack can be coupled with targeted attacks. So again, mass SQL injection is hosting compromise. They can directly embed the malicious script inside HTML, PHP, or ASP, or nowadays inside WordPress files. So it makes these injected content very hard to find. Sometimes, like the recent incidents, they were injected into database stored procedures or database-related code with WordPress or Joomla, which makes them very hard to extract, to find, and to remove. And then there are two other types of attacks that inject this that we saw a lot in the past, especially in Asia. And it requires no tampering of websites. When it happens on the lane, we typically see ARP spoofing using a tool like ZXARPs. This tool is very easy to use. It makes itself main in the middle in your lane using ARP spoofing. And so when people tell you that your website is serving malicious script, you go in and check all the content and there's no malicious script. And that's because they have not changed your website, but they've compromised your lane, and there's a tool acting as main in the middle. And then there's also Huang main in the middle. And that happened, for example, early March last year. It happened in the middle of the route for tw.msn.com, taiwan.cnet.com, and others. What happened was, in the middle of the route, a network device was compromised. Most of the traffic, because tw.msn.com is in Singapore, but it's accessed mostly from Taiwan. And so in the middle of the route, where most of the traffic goes through, one of the network devices was compromised, and it was injecting these malicious scripts into the packets and sending them back. Okay, so now we're going to do a demo. Sorry. So I'm going to copy this URL. It's a dig URL. And usually what happens when users view this dig URL is you would be taken onto a dig page, and you would see the dig content and who dug it and the comments, etc. Now, if we use the same URL, and we paste it into our Internet Explorer. Oops. Okay, sorry. Got to start mid-exploit first. So this is Drivesploit. We're going to start it. Okay, this is how to start our console. And if you need the source code, it is already available now at www.drivesploit.org. Now we've started the exploit, and let's just go exploit. Okay. And that would start the exploit. And now, as you can see down here, it's trying to access zcrack.org right here, which is not supposed to. What happens is the browser crashes, We go to the console again. And we see that we've started an interactive session with Meterpreter. So we can interact with the session. We can list out the processes. We can list the files. And then we can further then inject malware into this system. So let's just kill ourselves so that we terminate this connection. And we'll restart. Okay. So, but what happened when we visited zcrack.org? So if you look into this, the source code of zcrack, of dig.com. Oh, I'm sorry. What happened when we visited dig.com? Because it's a legitimate page. So here you can see it actually includes an iframe pointing to zcrack.com. Okay? So in this demo, and dig.com has fixed this vulnerability already, but this we injected this script before they fixed the vulnerability. So we used a persistent cross-site scripting vulnerability of dig.com to inject this piece of JavaScript, which then causes the browser to load content from zcrack.com, which is a malicious domain owned by us, which then exploited the browser and served Metasploit. Okay, so a bit of motivation behind Drivesploit. We provide solutions that detect malicious content in websites. That's a part of Armorize Solutions offerings. And we use multiple behavior and signature-based technologies. Most technologies are developed on our own, but we also integrate with antivirus, whose licenses are very expensive. And so we spend a lot of time testing our own technologies and selecting antivirus technologies. The key is, how good are we and them at detecting new drive-by downloads? And so we ended up studying a lot of drive-by downloads and writing a lot of server-side script to mimic the hacking tool's behavior in turning an existing exploit, for example, Aurora, or for example, the recent Adobe Zero Day, and turning that into a new exploit, exploiting the same vulnerability, but that bypasses antivirus detection. So then we figured out we need a good framework to help us replicate, refine, and manipulate exploits found in the wild. And so Drivesploit is born on top of Metasploit. In this type of attack, as you can see, the URL generators are JavaScript. The exploits and drivers are JavaScript too. The malware are PE binaries. So the malware part is often easier to detect due to two reasons. One, antivirus technologies are inherently better at detecting PE malware. And second is because these PE binaries get written to disk. And that's an obvious behavior to catch when you're monitoring for your system security. And so the playground is script languages. Why? Because we want to develop technologies and we want to select good technologies that can detect these JavaScript threats. Because when your website or when a customer's website is injected with malicious JavaScript, maybe 3 days later, the actual server that's serving the malware or the domain is already taken down. And so if the detector relies purely on PE binaries to detect this type of threat, then once the malicious domain, the actual malicious domain that's serving the malware is down, they can't detect anything because they can't actually fetch the PE malware for them to analyze. And JavaScript-based languages are also very, very hard to analyze compared to PE. And so here the playground is ECMA scripts, which include JavaScript, VB Script, Adobe JS, and ActionScript. And so we want to skip this last step and want to use Metasploit, want to serve payload in the form of memory injection. For example, Meterpreter. Okay? And so we're dealing now with, we're focused right now with just script obfuscation for both the exploit and also for the payload. Because right now, the payload is right here. We don't call it droppers anymore because payloads like Meterpreter inject themselves directly into the memory and they do all their stuff in the memory without having to write themselves to disk first. So drive-bys want to avoid detection at the victim's desktop, avoid detection by UTM and gateways, avoid detection by automated monitors, live for as long as possible. This is a very important requirement because when you're using 0 days in targeted attacks, you don't want any security vendor. Maybe you're just targeting 10 people. You don't want any security vendor to know this 0 day until a year later. So how do you do that? So conclusion, reduce exposure. Serve selectively. Avoid detection and analysis. Obfuscate well by obfuscating yourself well. So serving selectively. At the HTTP level, serve only to fresh IPs. So serve to each IP only once. This has become a typical drive-by-download behavior. So if you're a malware researcher, unless you're randomizing your IPs, otherwise, like if you're linking from an antivirus IP, they're just not going to serve anything to you. And this option is supported in Metasploit using the data store. And Metasploit supports different databases. Serving only to a particular referrer. For example, in our dig.com case, if your referrer isn't dig.com, that means you're trying to analyze me, and I'm not going to serve to you. If your referrer is dig.com, there's a higher chance that you're a victim visiting dig.com and then dig.com loading that iframe. And this option is also supported in Metasploit. Or a particular agent string. For example, if we're using IE 0 day, then we don't need to serve to Firefox or any other crawlers, Google crawlers, antivirus crawlers, whatever. And blacklist, which means we want to collect a big list of antivirus IPs, and if you're coming from Armorize, if you're coming from Symantec, McAfee, Trend Micro, nope, we don't want to serve to you. Okay. So dissecting an JavaScript exploit. There's a shellcode, there's a memory corruption, there's a heap spray, and there's a trigger. The shellcode is the payload, for example, Meterpreter. The memory corruption is where you corrupt the memory, for example, buffer overflow or other types of memory corruption, and you trigger that vulnerability. Heap spray is first published here at Blackhat by Skyline, and it's just an easy way, a very robust way to exploit the browser. And then there's the trigger, which is the trigger that calls your JavaScript, that calls all these code and activates them and executes them and triggers the exploitation process. So, and this whole thing that we just saw, all these JavaScript code is often obfuscated into a big blob of code that's unreadable and then deobfuscated to its primitive form. So we call the obfuscated form and the primitive form. So as you see in the previous slide, here's obfuscated form and here's the primitive form. So the attackers what they usually do is they try to randomize the primitive form. And they try to prevent the triggers from happening inside a detector. Okay, so two ways. First, obfuscate the primitive form to bypass antivirus detection. Second is if I am run inside a detector, I do not trigger myself. None of all the code is there, but it's not executed. So let's talk about the first one, which is the obfuscation, randomization of the JavaScript code. And the first one we implemented was called the JavaScript concat string obfuscation. It's very easy. This is how the payload looks like, and you call the obfuscate.js function inside Metasploit. And what it does is it randomly chops the string because this part. Okay, let me show you. Okay, so here you have script var shell raw equals a big long string, and you want to randomize this string. So what you do is, if you want to simulate this behavior, in Drivesploit, you call the function, and it randomly selects, it randomly chops the string up. You can specify, for example, chop every 3 to 10 characters. And then it assigns these chunks to different variables. And then it scrambles them. It scrambles these variables so that the assignments are randomized. Okay? So, randomized variable, and so basically, and then it concats them together. So this is what it does. It then adds them together to form the actual random string. The addition code here is also randomized, so there's no knowing which would happen first. And so this is the final code. So that's the first thing that we generated. Second is called JavaScript random text insertion. And it's a very used technique. It actually works very, very well. It takes a string as input, and you specify 648, as in this case. You're saying that insert a fixed 6-character random string for every 4 to 8 characters. So it returns a piece of JavaScript containing the injected string, and also a JavaScript variable name containing the reverted original string. So here you have a string. Drivesploit is fun. You call the injection function, and what it does is it generates a JavaScript along with the deobfuscation JavaScript, right? So it generates this string, assigns it to a variable. It also generates the regular expression deobfuscation to take out the randomly generated and inserted string. The third one is called JavaScript random text insertion. And this part is also very important because the numeric literals inside a piece of JavaScript is often the target for antivirus detection. It's often used as signatures. So for example, in the IE drive-by download exploit that we're using as example, there is a hex number that's fixed inside the exploit. And so what you do is you call the Drivesploit function, and it turns that into an arbitrary algorithmic calculation, as you see here. And this results in this number right here. All these are techniques that we've seen in the wild, and so we just want to know which antivirus is good at detecting which, and how good are we at when something like this happens. So with this type of framework, what we can do then is when a new exploit comes out, we can expect that all antiviruses after a week, or most of them, are going to be able to detect that because that's becoming a new, an old exploit. But we want to know the ability for these technologies and for our own to detect new and derived exploits. So we take that exploit and we'll put them into Drivesploit, and we will call these functions, and Drivesploit would then serve variations of the same exploit, which works, and see who can detect what. Okay, and now to the latter part, which is trigger prevention. And these are just some techniques, but they work very well. div unload. So setting your trigger function in div unload. And why that works is a lot of automated detection engines use JavaScript engines such as SpiderMonkey or Rhino that does not implement the DOM. And so when you're setting div unload without the DOM, it's not going to trigger. And the second one, for example, image unload. Anybody want to guess which one's more effective at beating antivirus? Div unload or image unload? Why? Why? That's correct. But why? Okay, so some vendors like us actually run instances of IE like the virtual machine that I just showed you, and they monitor the behavior. However, some of them, including us originally, in order to, because we have to scan millions of URLs per day, so in order to speed that up and to lower the cost, we configure IE to not load images, and they figured this out. So you can run a real IE, but if you disable images to save some bandwidth and to save some computation power, it's not going to trigger, right? So this one, do while. A lot of them use grammatical differences between IE and Firefox, or IE and scripting engines available. So this one, there's a semicolon right here between the bracket and the while. It's not that obvious, but this is actually a grammatical mistake. And so Firefox-based JavaScript engines like SpiderMonkey and Rhino would actually raise an exception here, but IE can take care of it perfectly and keeps on executing. So if you put this in, then in an automated detection by a security vendor, it might just raise an exception, while only vendors that run the actual IE would be able to keep running the code. And then browser fingerprinting, which is very, very effective, and which I'm going to show in a bit. So testing it out. So the plain, the one that we selected, the plain exploit, hits 17 out of 42 in virus total. Randomized vars. I didn't talk about this. We implemented a JavaScript parser that parses the JavaScript, your JavaScript automatically. So you call the function, give Drivesploit the JavaScript, and it will parse the JavaScript, and then it will extract all the variable names and function names. And that's a very formal parser. And then it will replace all your variable names and function names with random names for you. So it's basically what we call random vars. It's a random variable JavaScript generator, okay? And works very well on existing JavaScript. Unless you have a grammar error, then our parser breaks. And that, however, we were 17. That took us down to 16, and that's why I had no slide for it. So apparently, all the signature-based technologies were not basing their patterns on variable names. So injection source code, so the string injection took us down to 13. And random vars plus concat on shellcode plus injection on shellcode brought us down to 11. So all those 11 were not detecting the payload at all. They were detecting the heap spray or the memory corruption JavaScript instead of the payload. So I think after we've added all these options together, and we still have 11 left, all those 11 were detecting other JavaScripts and not the payload itself. Okay. So we do a concat on the actual code. We end up with 1. And on the heap spray and the memory corruption code, we do a concat on that. We end up with 1. We do an injection on the shellcode, or the payload, and concat on the actual code. We end up with 0. Okay? So before this, all of this, we were manipulating the shellcode, or the payload. And that brought us down to 11. But manipulating the actual heap spray or memory corruption JavaScript brought us very quickly down to 1 or 0. Random vars plus injection plus concat, also 0. However, VirusTotal runs the command line version of antivirus. These versions are typically for vendors like us or for network vendors, email servers, load balancers, web caches, what have you, any kind of device that wants to have antivirus capability. And these console versions are actually very weak. The desktop version is much stronger. The reason is because the desktop version can monitor the host environment. So it can hook into browsers. It's easier to get the raw form of exploit, because if your browser decrypts the raw form out, then if I'm monitoring everything that your browser is doing, if I'm hooking into the JavaScript engine, then I can get the raw form. And then I can also do behavior analysis, because, for example, I can do buffer overflow analysis. If you have segments of executable code in data segments, for example, that's very obvious that it's a buffer overflow. And we can also monitor for download to file behavior. So this is a test on some of the using some of the bigger antivirus vendors. Didn't really list out the names, but you can guess. We used to give a lot of talk in Asia, and they weren't particularly happy when we list out the full names. And these are the algorithms that we used. So plain, for example, 2 antivirus didn't even catch the plain, so that wasn't. But right here, you see this antivirus didn't catch anything but catch concat code, because they just figured that if you're concatenating a lot of strings, then that's probably malicious, right? So that's a heuristic that worked for them. While for this vendor, it worked. All of our manipulation against the shellcode didn't bypass them, but once we started to concatenate, to obfuscate the other parts of the JavaScript, we actually got a bypass. And for this one, this vendor was very, very good. It went on to the last 2, which is injection against shellcode, concatenating the shellcode, and also fingerprint. So let's do a demo. Okay, so let's start our Drivesploit again this time. Let's use some parameters. So I want to use random variables. And I also want to use, I want to also concat the shellcode. sorry, true. And I also want to obfuscate using concat the rest of the JavaScript. Exploit. Start the exploitation process. Go into our VM. Let's just link directly to zcrack. Okay, so let's try clicking on remove. It's still detected after 3 options set. But although we click remove, actually the heaps rate is still going on. It's not effectively really killing the exploit. And so as you can see here, a session started in Meterpreter, meaning that our VMs connected back to us. So this is the VM. And so let's connect to this session and list the processes. We can list the processes. We see Internet Explorer listed as 3092. So let's just kill that for them. And that kills the VM's Internet Explorer. And so we have full control over this VM, although the antivirus did alert, didn't kill it, but we don't want it to alert, right? We want to completely bypass it. This is one of the best ones for drive-by download detection already, by the way. So this time, let's set. We still want to use random vars. And this time, let's use injection for the shellcode. Insertion. This injects arbitrary commands, arbitrary strings. Oops. Doesn't matter, actually. And let's use concatenation for the rest of the JavaScript. Exploit. See what happens. This time it didn't alert. With antivirus desktop versions that has behavior monitoring or HIPS, host-based intrusion prevention systems in place, sometimes it's a bit of luck. For example, if you're doing heap spray for too long and notices that something's going on and you're allocating too much memory, it may alert. But in this case, it hasn't alerted. And we are with a new Meterpreter session. Again, let's kill the Internet Explorer for it. Here we go. Okay, so that's the demo for bypassing desktop versions. And that one was listed here, as you can see. Not very easy to bypass. And then we add another section. This vendor is very interesting. It appears to be one of the vendors that really properly implemented HIPS, host-based intrusion prevention system. And so there are 2 columns. So for example, when we dump these exploits to a bare HTML file, and we ask it to scan the file, here's what happens. It doesn't have a lot of signatures, and it's not very good as these guys. These guys, it doesn't matter. These guys over here, actually, it doesn't matter whether you're loading content from a web server or you ask it to scan the bare HTML. It's some heuristics and everything put together, and they'll just detect. But for this vendor, if you're asking to detect static HTML, it doesn't have a lot of signatures. But when your browser loads and it's actually doing heap spray and it's trying to corrupt the memory, it detects all the time. And we'll tell you that. But however, it also has sometimes it has false positives. When you run commercial programs that are packed, it also alerts you. So that's a drawback. Okay, finally, last technique, behavior-based fingerprinting. So if we submit a behavior-based fingerprinting Drivesploit to a detection like whip-a-wet, it doesn't detect anything. But there's actually malicious JavaScript. What happens is, for example, when you use Mozilla and you alert it out, it alerts nothing. But when you use the correct browser that we're trying to exploit, it alerts the actual script. What happens is, here is browsers actually have very different implementations from each minor version to each minor version. And so we have implemented code that correctly fingerprints browsers based on these minor differences. Parser differences, CSS rendering differences, JavaScript engine grammar differences, for example. And so, it's this, we built code that can very precisely fingerprint which browsers are actually running the piece of JavaScript. We've implemented these functions. So use browser features as and then each checker actually generates 1 bit of the key. Okay? But however, each checker, every time when we serve the Drivesploit, the checkers are randomized. So bit 1 isn't always going to be the same checker. Okay? We randomize the order, and then we generate all the JavaScript checkers, and then we'll, of course, obfuscate the JavaScript. And then finally, you can use an option to set. For this Drivesploit, I only want IE6 to be able to decode it. Okay, then we will encode it. We'll randomize the checker orders. We'll generate these checkers for you, and then we will know what these checkers results are in IE6, and then we will generate the corresponding key in advance for you, and then we will encrypt. Our entire JavaScript using this key. So the only way for browsers to be able to correctly decode this is if it's actually running on the correct browser. Any type of automated detection, JavaScript engines, what have you, would all fail. And it's very hard for security researchers to analyze. And we've encountered quite a few of these with very fancy encryption algorithms, mostly in targeted attacks. So it defeats most automated detection mechanisms. We can try brute forcing the key, but then there's actually, you can put a time to it. We don't have time to explain this, but it's actually very hard. Because I can first serve you something to decrypt. You have to decrypt, give me the key first, and then I give you the actual script. And this key is invalidated after, for example, 2 minutes. So unless you can brute force in 2 minutes' time, otherwise it's not going to work. So why not antivirus? Why is it so hard for antivirus to detect the drive-by download threat? Well, antivirus is designed to install on desktops and notebooks. So on desktop and notebooks, there are a lot of very complicated behaviors, a lot of apps, a lot of heterogeneous apps installed, and it's very resource constrained. And therefore, antivirus and gateway vendors typically rely on signature-based pattern matching technologies that are lightweight and accurate. So for example, antivirus typically operates under the restriction that it's going to be very robust on the notebook, and it's not going to use more than 50% of your notebook's computation power, right? Versus, and that's why it's not very good at detecting these write-by-download attacks. Vendors like us, we have the privilege because we are crawling your website, we're scanning every URL in your website, and we can take as long as we want to finish our scan, and it's not going to impact your notebook's performance. So we're using totally different algorithms compared to antivirus. And because of and it's also because of the nature of drive-by-download attacks, they're disposable JavaScript, disposable PDF Adobe JS, disposable Flash Action Script. But so what? Well, these disposable scripts, first, it's so easy to obfuscate, as we've shown. And second, very importantly, JavaScript packing is a norm. Right? People love to pack their JavaScript. A lot of commercial JavaScript are packed. You have to buy these JavaScript, and you tell them which URL you want to use the JavaScript in, and it has all these encryption keys locked into it. So, and Google has their JavaScript packer. Yahoo promotes their JavaScript packer. And so you can't just say, okay, this JavaScript is trying to unpack itself, then it's probably malicious. So if, for example, Drivesploits, all these Drivesploit packers, somebody sets up a website and says, submit your JavaScript, will pack it for you, and it becomes very widely used, then it's going to become even harder for antivirus to detect what's been generated. Okay, so antivirus don't work. How about behavior-based approaches? Okay, Honey Client, Sandboxes, SpiderMonkey, Rhino, JS Unpack, Webpack Web, Python, and Python Honey Client, for example. Well, it's very easy. First of all, we haven't shown here, but instead of generating JavaScript, we generate VB script, and most automated detections are based on some versions of SpiderMonkey or Rhino, and that doesn't execute JavaScript unless you want to implement your own JavaScript engine, or just don't serve to detectors, like the feature we talked about previously. Serve once per IP, blacklist Google and security vendors' IPs, detect agent strings, detect, so all of these can be used. And also browser-aware packing, which is the browser fingerprinting. And very little but effective techniques. Sleep for 30 seconds before you exploit. If you're scanning millions of URLs a day, you can't afford 30 seconds per URL. You're not going to finish. And therefore, if you sleep 30 seconds before you exploit, well, chances are that they terminate execution before you actually do anything. Or time lock puzzles, and we don't have time to show this. This is basically, you would do some algorithmic calculation. You would need to spend certain time. You would need to spend 20 minutes in order to calculate out the right results, in order to decrypt your JavaScript. Then the antivirus vendor would just need to spend 20 seconds. And when you're a crawler like Google, you're trying to crawl the entire web, you don't have 20 seconds per page. And that pretty much concludes our talk. Finally, regarding the thread itself. Script-based exploits are going to persist for some while. Flash, PDF Flash, VB script, Flash inside VB script. It's seen since 2001, but it flourished since 2004. Started out by mostly used in targeted attacks. And there's a Chinese word for it starting very long ago called guama or wangma, which is what I had on my slide. That was way, way before the drive-by-download term came about. Since 2006, threat analysis of this type of threat has been harder because crime groups and hobbyists became very active. So it's very hard now to differentiate attacks coming from crime groups, hobbyists, and targeted attacks. When you're analyzing targeted attacks, that takes a lot of time away from you because you got to clear out a lot of the logs. A lot of the very good techniques and attacks today are not are not a part of targeted attacks, but rather crime groups and hobbyists. Cross-use of tools. Now targeted attack groups and crime groups and hobbyists cross-use each other's tools, which makes threat analysis harder. Sources of info include DNS information, forensics data, historic data, tools, fingerprints, and intelligence exchange, which is very important. Drive-by kung fu, drive-by techniques, only makes a small part of the success of a drive-by download attack, actually. Targeted drive-by attacks are almost always coupled with social engineering. Okay, so, and that's why it's called targeted attack. So if you know your victim's daily behaviors, if you monitor their emails and phone calls, he calls somebody and say, send me this email, then you send him that email, you're the attacker. That's called a targeted attack. And it succeeds because you are very good at social networking, not because you have some fancy skills. Well, you do because you need to bypass this in the virus, but that part is much easier. And then, for example, a lot of times you can release some information, release a critical PDF that contains very, very critical information that this guy has to open. He knows it's malicious, but he has to open it. Okay, so it depends on how good he can contain it. And that ends our talk. Thank you. You can follow us on Twitter. You can go to www.drivesploit.org and download the source code. The slides will be available as soon as we finish our DEF CON talk. Thank you very much. Thank you.